was telling folks in the classroom that I must be a little excited tonight about this class because I started the live stream a full minute early. So if you're just tuning in on YouTube and you say, hey, wait, they've started, well, yeah, and it's my fault. But anyway, we're very glad to have you here. My name is Gary, ham radio call sign W4EEY, or in phonetics, Whiskey 4, Echo, Echo, Yankee. And this is the beginning ham radio class. We have a classroom full of Zoom participants who are ready and eager to join us this evening. And if you're watching on YouTube, you can play along as well. And very happy to have you here. Tonight we're going to go over Chapter 3. And when I say that, I always grab the book. This is the book we're using. It's the Amateur Radio Ham Radio License Manual from the American Radio Relay League. This is the 5th edition book. This is a new book that came out July 1st. And the reason it came out is that all of the questions in the back are all brand new this year. So if you have an older version of this book, it's got the old question pool. And it's not as helpful as it could be. So just bear with us, and if you can, get the new book and join along, and you can get your ham radio license. All it takes is passing a 35-question multiple-choice test, and we'll even tell you how to get your testing session going, etc. So if you'd like, watch the YouTube playlist for the previous classes, and you'll get all caught up. All right, so take the headphones off over here. Chapter 3. This is the most difficult chapter probably in the Technician series, especially for those who have not been involved at all with electricity or electronics. And it's like learning a whole new language. I mean, you jump in and you go, what the heck are they talking about? And you have this feeling like, I'm never gonna get this. I want you to know that feeling is completely normal. You're normal. That's what happens when you are first exposed to this information. But over time, as you read the book, as you watch some videos, as we talk about it here tonight in class, I think you're going to have some aha moments. And those are those moments when you go, oh, that's what they were talking about. Oh, that's what that means. So don't worry about it if you're feeling a little lost. That feeling is completely normal. And I have to say that in this class, in the technician class especially tonight, the subjects that we're covering could easily be semester-long classes at college or junior college. Semiconductor devices, active devices, passive devices. And we're going to cover them all tonight in 2 hours. Well, we're going to skim the surface, let's put it that way. So before we get started, I always ask, is there anyone who has any questions tonight about any of the material we've covered so far? All right, I don't see anybody unmuting, so we'll go ahead and get started with Chapter 3, Section 3.1, Electricity. And we start with the basics. Insulators versus conductors. What conducts electricity, what's a good conductor, and what inhibits the flow of electricity. And when we hear the word insulator, at least I think of these devices which are used to insulate high voltages from one point to another. They're manufactured especially just to not conduct electricity. Whereas the opposite, wires, are the common conductors of electrical current, copper wire, aluminum, etc. And so we have conductors and insulators. That's where we're starting tonight. Conductors conduct electricity kind of like this. And it's because that copper and aluminum and other metals have free electrons in their outer shell. And those free electrons may be moved along by force, voltage on one side, and you get a current flow through a conductor. So you see here the electrons, the minus charges there, are moving along from left to right. Likewise, here in an electric circuit, this is a schematic diagram. A schematic diagram is shows you how components are connected together. And it's pretty simple. We have a battery there on the left, and we have a lamp on the right, and we have at the top a switch, a single pole, single throw switch. And when the switch is closed, you'll see that electrons move from the minus terminal on the battery to the plus terminal on the battery. I don't mean to confuse you, but there are two theories of current flow. In older books, mostly dealing with vacuum tubes, they talk about electron flow. But today, with integrated circuits and solid-state devices, we talk about current flow, and we say current flows from positive to negative. So not to confuse you, but this is correct as far as electron flow. So some key concepts, as you might have read in the book. Voltage is the pressure that moves electrons through a conductor. Current is the flow of the current through the conductor. I always like to think of it as kind of like a turnstile at a baseball game, and people go through and click, click, click. Well, that's the current flow of electrons through the wire. Resistance is opposition to the current flow. The symbols, by the way, the pressure is volts, the current is measured in amperes, and the resistance is measured in ohms. And power is the rate that energy is being used, and that's measured in watts. And a circuit is any path through which a current can flow. I'd like to take credit for this drawing, but Dave Ivey actually found it online, and there's the original source and the URL on the bottom. So volts is the pressure that is pushing the current, the amps, through the wire, and Mr. Ohm up top is the resistance of the wire that is resisting the flow of current. So if you like to think visually, here's a pictorial for you. And a table to review that the voltage in the Ohm's law formula, it's E for electromotive force, but it's measured in volts. It's the pressure that triggers electron flow. Current in the Ohm's law formula is I for intensity in French, and it's measured in the amperes, and it's the rate of electron flow. And resistance is R in the Ohm's law formula. It's measured in ohms, and they say it's a flow inhibitor. It's also indicated by the Greek letter omega. So DC versus AC current. Let me turn on my little laser pointer here. All right, so here we have a graph representing voltage versus time. And with a direct current voltage, DC voltage, we're going in the positive direction. So here we have a positive voltage and it stays the same. So a DC voltage is that which you would get out of a car battery, for example, or a D-cell battery for a flashlight, or some sort of power source for DC power. AC, or alternating current power, actually makes a start from 0 volts, in this case going negative, coming back to 0 volts, going up to positive, and back, up and down and up and down. This is what is coming out of your house wiring when you plug a lamp or a device into the wall. We in the United States have nominally about 120 volt AC, 60 cycle AC power. This happens 60 times a second, or 60 hertz, 60 cycles per second, the alternation. So DC and AC, the differences. Now, question for you. What do you think? Is this AC or is this DC? Let me just point out, here's the 0 line as we looked at before, and notice that the waveform never goes negative. It never goes down here. It's always going positive. This is actually known as pulsating DC. And so this is actually a direct current. It's not a very smooth direct current like you get out of a battery, but it is in fact DC. And schematically, on a schematic diagram, you might have a DC battery. You have a load, which is indicated by a resistor, and you have current flow from the battery through the load and back to the battery. With an AC circuit, you have an AC generator. It could be from Duke Energy or some other power provider. And what happens is that current flows in the resistor in this direction, then it flows back this way, and so forth, all the way around the circuit, back and forth, as the AC voltage swings from positive back to zero down to negative. And we mentioned that batteries chemically store DC energy. And if you look in your book on page 5-18, there's a table of various different kinds of batteries. And something to note that alkaline and carbon zinc batteries are not rechargeable, whereas nickel metal hydride, lithium ion, lead acid gel cells are all rechargeable batteries, meaning that you can take a power source and put electrons back in to the chemical storage in those batteries. So the most basic law or rule in electronics, and one that technicians use every day, came from this gentleman, George Simon Ohm, who a German physicist from 1789 to 1854. And I have an interesting story about Mr. Ohm. I was sent overseas when I worked for the Voice of America and was stationed in Munich, Germany, the period from 1990 to 1993. And during that period, I had to attend an event at a church in downtown Munich. And in order to get to the event, we had to walk through a cemetery. And as I'm walking through the cemetery in Munich, Germany, I tripped over a grave that had a raised border. It just so happened to be his grave. He's buried in Munich, and you can see his headstone there on the lower right. Anyway, George Simon Ohm is responsible for Ohm's law. Now think back to last week. We saw this pyramid. You might remember it. It had to do with the relationship between the speed of light, 300 million meters per second, and the frequency in megahertz and the wavelength in meters. And we determined that if you had 300 in the top, you could determine the wavelength by dividing the frequency in megahertz into 300, and you'd come up with the wavelength in meters. Well, very similarly, we have the Ohm's law pyramid. And what this is a way to indicate if you know two of the variables, you can find the third. And you have to kind of stick your thumb over what you want to find. So pretend my thumb is right here over the E. I want to find out what the voltage is. I know the current and I know the resistance. So you can multiply the current in amps times the resistance in ohms, and it will give you the voltage. Also, if I want to find the resistance, I cover this up with my thumb, and I know that it's the voltage divided by the current, E over I. And if you want to find the current, it's E divided by R. So this pyramid translates into these three equations, but it's usually easier for folks to remember the pyramid. So I call this the EIR, or the ear pyramid. There's another one from Watt, another physicist, known as Watt's law, and that is with power in watts over current in amps and voltage down here. So if you want to find the power, cover that up with your thumb, it's I times E. So current in amps times voltage will give you the power that a device is using. Or if you want to find the voltage, you can take the power and divide it by the current. So here are the two most basic formulas that technicians around the world use every day. And in fact, it has practical application. If you've got a refrigerator plugged in and you know it uses 300 watts, and you want to know what kind of current is coming out of the wall, well, you can take 300 and divide it by 120 for the volts, and it'll tell you the amount of current that refrigerator is drawing. So this is a very practical set of formulas that you really kind of need to memorize. The ear pi formulas. Sounds funny, but okay. Ohm's law and Watt's law. Now, I don't want to scare you, but from these two pyramids, you can derive all of these formulas. You don't need to know these formulas, but I want you to know that they exist. And you'll get this PDF linked, and you can take a closer look at this at your leisure. So a series circuit, and this is in pictorial form. It's a circuit connected here using copper wire, because copper is a good conductor of electricity. Why? Because it has an excess of electrons in the outer shell of its atoms. And note the switch up on top. So when the switch is closed, current will flow from the battery through the switch, through one light bulb, through another light bulb, and through another light bulb until finally it comes back to the battery. So these three bulbs are said to be in series. This is the standard Christmas tree light string, that when one of the bulbs goes out, none of them light up. That's a series string. So this is a series circuit, and this is in a pictorial form. In a schematic form, you could redraw it something like this, although the switch isn't there, but a battery and then the various loads that you have out and then going back to the battery. So that is a series circuit where you have the loads connected one to the other. A parallel circuit is like this, pictorially. You have a power source, in this case a battery, and you have your bulbs again, but instead of being in series with each other, each of them has their own independent circuit that goes back to the power source. So in this case, if a bulb burns out, the other two will continue to function. So this is a pictorial look at a parallel circuit, and here's a schematic representation of a parallel circuit. I'm just reaching over there to push a button. All right, so here we have the battery source and the various loads that have their own independent circuits back to the power source. So this in this new question pool, this is not emphasized as much, but we have, in this case, both series and parallel connections, and they ask in the past what happens at the junctions. This is called the series junction, and this is called the parallel junction, so I had to use petticoat junction. In a series circuit, the current through one device is the same as that through another device. In a parallel circuit, the current divides between the two. In a series circuit, the voltage across these divides up, whereas in a parallel circuit, the voltage stays the same. We'll talk more about this here in a second. So in a series circuit where resistors can be used in this way, if they're equal value resistors, and let's say we have 10 volts coming in here, the voltage here will be 5 volts. It's a voltage divider. And you can come up with a different voltage by varying the ratio of these resistors. So in a series circuit, there's a voltage drop across one resistor and a voltage drop across another. Whereas in a parallel circuit, the voltage here, 12 volts, it's the same across each one of these components. 12 volts across this one, 12 volts across this one, and 12 volts across this one. Don't worry if your brain is starting to hurt here. And it's been a long time since I was thinking about, I've been involved in electronics for over 50 years now. So sometimes I don't have the same sensitivity that you have to this new material. So if you got to scream out and say, hey, I don't get it, feel free to do that, and I'll stop and we'll try to explain a little better. So you hear the term a short circuit. What is that? What's a short circuit? Well, here we have a battery and a lamp, and we're supposed to be lighting the lamp, but if a piece of wire were to fall across where the lamp is, the resistance of this wire is very low, and so all of the current will flow through this short circuit and the lamp will not light. So that's a short circuit. A closed circuit is a normally operating circuit, and an open circuit is when the wire comes off. So those are just some definitions of short circuit, closed circuit, and open circuit. A lot of material. A meter. We use meters all the time, and what it basically does is display an amplitude on a numbered scale. And that numbered scale could be an analog scale like here. This is from 0 to 30 volts. Or it could be a digital readout, such as this, which is reading 12.85 volts. But both of these display an amplitude on a numbered scale. And when we're connecting a meter, we always connect an ammeter, something to measure the current, in series with the circuit. Remember I said it was kind of like the turnstile at the ballpark? We want to count all of the electrons crossing this point, so you put the ammeter in series with a circuit, whereas a voltmeter is measuring the pressure across a device, and so you want to have it in parallel with that device. So this is how we can measure the current going into the lamp, and here we can measure the voltage across the lamp. Ammeters are in series, voltmeters are in parallel with the device under test. And meters, probably the first piece of electronic test equipment you will ever buy, and you'll probably buy one because they're handy in ham radio, is a multimeter, also known as a volt-ohm milliamp meter. They come in different flavors, analog style here, digital style here. And you want to get a good one because you want to have a reliable piece of test equipment. So nothing against Harbor Freight, but don't buy a Harbor Freight digital voltmeter. Buy something nicer, well, Fluke is probably considered the best, but they're also probably the most expensive. Okay, now brace yourself. This is not in the book, but I have to let you in on something that has been a secret that is well known among technicians over the ages. And that is that electrical devices actually operate on smoke. No kidding. We don't want our devices smoking. Have you ever seen a radio or TV burn out and all of a sudden the smoke starts coming out? This is a humorous way to point out that you can buy a multimeter, but if you don't use it properly, you can let the smoke out of the multimeter. This meter can measure volts, amps, and ohms, but if you set the multimeter to read ohms and you're putting the probes in a powered circuit, you'll end up burning out the voltage divider resistors inside the meter. You'll let the smoke out. So that's the secret. And you'll actually see this talked about a little bit, that don't let the magic smoke out in electronic circuits. And don't hook your ohm meter up into a powered circuit, or bad things will happen. And if you're using a multimeter, make sure that it's rated for the voltages that you want to measure. If you've got a 240 volt circuit, but your meter's only good up to 100 volts, well, that's no good. Or in really absurd cases, if you want to measure a 5,000 volt circuit in a power amplifier, you need a probe, something like this, that is designed for your safety and to make sure that the meter itself is not damaged. So make sure that you're using a suitable meter and suitable probe for the measurements that you want to take on. This is an interesting case. We'll talk about capacitors here in a little bit, but capacitors are essentially two plates, metal plates, that are separated by an insulating material. And when current flows through the capacitor, electrons build up on one plate and the absence of electrons on the other until the capacitor is kind of charged up like a battery. So what happens is that if you hook an ohm meter into a circuit, well, let's look at this circuit first. So here we have a battery and we have a capacitor, and a capacitor, depending on its value, depending on how big it is, will allow current to flow through it while the electrons build up on one plate and the absence of electrons on the other. So there will be a brief bit of current flowing, and guess what? The light bulb will light up briefly. So that's one way you can actually test a capacitor. Also, you can test capacitors with a resistance measurement on your multimeter. If you have the power removed from the device and you put your meter in a circuit and you find a low resistance that later rises to a high resistance, that tells you that you're probably measuring the effects of a capacitor in the circuit. We made it through the first section. Okay, let's see what we learned. If you'd like, go ahead and unmute if you have an answer and tell us what you see here. So electrical current is measured in which of the following units?
D, amps.
Everybody agree with that? I'm going to go ahead and spotlight that so that it doesn't go away when people talk. All right, amps is correct. And electrical power is measured in which of the following units?
B, watts.
Power is measured in watts, indeed. All right, let's hear some new people here. What is the name for the flow of electrons in an electric circuit? Current, indeed. D, current. Oh, we had a question last night in the general class, and I want to emphasize it here, that we talk about, these answers and the questions, and we say A, B, C, or D, but on your test, when you take it, these are going to be rearranged. They're not going to be in the same order. So don't memorize A, B, C, or D. But if you can, try to remember what is exactly the correct order, so or the correct answer, not the letter. Okay. What are the units of electrical resistance?
Ohms.
C, yeah.
Ohms is correct. That's resistance. And what is the electrical term for the force that causes electron flow?
Amps.
Nope.
Volts.
Volts is the pressure. Amps is the current. So the electrical term for the force that causes electron flow is voltage. It's also called electromotive force, or EMF. So why are metals generally good conductors of electricity?
E.
They have many free electrons in the outer shell of the atoms, indeed. And which of the following is a good electrical insulator?
A.
A
No, B.
is a very good conductor.
Oh, insulator. Sorry.
Insulator would be
Glass.
B, glass, indeed. And which of the following describes alternating current?
That would be alternating as C.
Notice A, it says alternates between a positive direction and zero. That's pulsating positive DC. B says current that alternates between a negative direction and zero, so that would be pulsating negative DC. So the correct answer is in fact C, current that alternates between positive and negative directions. So which term describes the rate at which electrical energy is used?
Power.
Power indeed, and it's measured in watts, correct. And how much current is required? Okay, now we're going to do some practical applications of Ohm's law. So you can even write out that Ohm's law pyramid, EIR, in front of you to help you out. So how much current is required to deliver 120 watts at a voltage of 12 volts DC? So this is from the Watt's law, or the pi pyramid.
B, 10 amps.
So power is 120 watts, and that's on top in that pyramid. And if you divide 12 into 120, you get 10 amperes. That's it. So what formula is used to calculate the current in a circuit?
Current.
E.
So the French, call the current the intensity. So I is current. And what did you say? I'm sorry?
You said
The
B
measure.
divided,
B, boy, indeed.
Bravo.
Yes, okay.
divided, yeah.
Yeah, very good.
Shit.
Yeah, Zoom is kind of distorting you there a little bit, so that's good. So current equals the voltage divided by the resistance. And what formula is used to calculate voltage in a circuit?
I times R.
I
Yes.
times R is equal to the voltage. Correct, absolutely. And what formula is used to calculate resistance in a circuit?
Bravo.
Does everybody see that? EIR is the Ohm's law pyramid, and you're trying to find R, so you put your thumb over the R.
A.
No, and you're left with E divided by I. So he was right. B is correct. R equals E divided by I, or E over I. All right, so what is the resistance of a circuit in which a current of 3 amperes flows when connected to 90 volts? So we're looking for resistance.
30 ohms.
So how did you get there?
It's 90 over 3.
Absolutely correct. E over I, or 90 divided by 3 is 30, correct. And what is the resistance of a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps?
18 ohms.
Well,
Times it.
how did you get that? No, because
I
you're
think
looking
he's
for
right.
R, so you go back to that pyramid.
No, he's wrong.
You take, and so R is equal to what? E divided by I. So
13,
12 volts,
13.5.
12 volts divided by 1.5
Oh, it's divided,
amperes is 8 ohms.
Yeah.
12
Oh, shit, I was-
divided by 1.5 would give you 8. All right, and what is the resistance of a circuit that draws 4 amps from a 12 volt source? So we're looking for R.
A.
So R is equal to E divided by I, or 12 divided by 4, A, 3 ohms. Correct. And what is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? So we're looking for I.
$1.5 amperes.
120 volts divided by 80 ohms is 1.5 amps, indeed. And what is the current through a 100 ohm resistor connected across 200 volts? So we're looking for I.
C. 2 amps.
So I equals E divided by R, or 200 divided by 100,
So
2 amps. Correct. And what is the current through a 24 ohm resistor connected across 240 volts?
10 amperes.
I,
240 divided by
we're
24.
looking for I, so 240 divided by 24 is 10. These are pretty mathematically easy things. You just got to keep the formula straight in your head. All right, so what is the voltage across a 2 ohm resistor if a current of 0.5 amperes flows through it? So you're looking for E, voltage.
I say 1 volt. Don't you multiply that one?
Correct.
Problem.
E equals I times R, so 2 times 0.5 is 1 volt. And what is the voltage across a 10 ohm resistor if a current of 1 ampere flows through it?
Ten.
You're looking at, for E, so it's I times R, 10 times 1, 10 volts. And these are true. So if you've got a circuit and you can make a measurement, and you can calculate with the current or the voltage or whatever else, if you can figure out what the measurement is. So what is the voltage across a 10 ohm resistor if a current of 2 amperes flows through it? So we're looking for voltage.
Delta.
D.
Everybody agree? 10 times 2 is 20. All right. And in which type of circuit is DC current the same through all components?
Series.
In a series circuit, the current is the same, exactly. And in which type of circuit is the voltage the same across all components?
Parallel.
That's
Yeah,
a
B.
parallel. That's a parallel circuit, indeed. And which instrument would you use to measure electric potential?
Voltmeter.
Electric potential, also known as electromotive force, also measured in volts, that you need a voltmeter. Exactly. Electric potential kind of sounds like pressure. So, how is a voltmeter connected to a component to measure applied voltage? How is a voltmeter connected?
In parallel.
In parallel with the device under test, indeed. And when configured to measure current, how is a multimeter connected to a component?
In series.
This is the turnstile. You're measuring the electrons going by, so it's got to be in series with the circuit. And which instrument is used to measure electric current?
C.
So
Voltmeter.
current,
Ammeter.
yeah, you're measuring amps, so it's known as an
Ammeter.
ammeter.
Oh,
Yeah, and it's
current. All right.
connected in series. Yes, indeed. All right. Which of the following can damage a multimeter?
Attempting to measure resistance by using voltage setting. Voltage.
Almost. But think about it again.
Charlie.
Attempting to measure voltage.
Measure voltage. So, but if you're going to measure voltage, that implies that the circuit is powered up. The power, there's power to the circuit, and you're trying to measure voltage, but you've left the meter in the resistance setting. That never happens, does it? To everybody. Yes, indeed. And what happens when you do that is you let the smoke out.
Let the smoke out.
So don't do that. Which of the following measurements are made using a multimeter?
Voltage and resistance.
D.
The only thing we've talked about is voltage and resistance. Those are the only things. It doesn't measure impedance or reactance or signal strength or noise. So what reading indicates that an ohm meter is connected across a large discharge capacitor? This is that oddball circuit when you put the meter in there and it reads low and then starts coming up.
D.
Now, actually, it's A. You put it in there and you have a low resistance and then it starts coming up and up and up and up and it becomes a higher resistance. So increasing resistance with time.
Okay.
This is a troubleshooting technique. Some people use this, some people don't. But it's part of the test. So which of the following precautions should be taken when measuring in-circuit resistance with an ohm meter?
Ensure that the circuit is not powered.
Yes, or you will let the smoke out. Yeah, exactly. So which of the following precautions should be taken when measuring high voltages with a voltmeter?
That would be B.
Yeah, remember that big honkin' probe I showed you there? Ensure that the voltmeter and leads are rated for use at the voltages to be measured. Ladies and gentlemen, you made it through the first section of our chapter. And so what we're going to do right now, we're going to take a 5-minute break. and we'll have a countdown timer on YouTube, so you can get up and stretch and move around a little bit, and then we'll be back to finish off the chapter. You're doing great. I'm so proud of you. So hang in there, and we'll be right back.
Okay.
Okay, and we are back. Welcome back to the Bat Cave, or the little mini studio I have set up here in my office in the house. Very happy to have everybody back. We're going to be continuing on with Chapter 3 in the Technician License Manual. And we're going to be talking about components and units. So we've already talked a little bit about resistors and resistance. Resistors oppose the flow of current in a DC circuit. Oh, I'm going to take my spotlight off so you don't need that. And I can see you a little bit better if I do that. Okay. Resistors are measured in ohms. So resistors oppose DC current flow by definition. And an interesting phenomena is that with an AC signal, voltage and phase across the resistor are in phase. That isn't necessarily important to you right now, but it will be in the future. And resistors are typically indicated by a color code with different bands that tell you the first two digits of the resistor and a multiplier, so you can tell whether it's a 100 ohm resistor or a 1000 ohm resistor, depending on the colors on that resistor. And you can also have variable resistors, also known as potentiometers, what we used to call volume controls on radios and TVs. Now everything is digital, and so you're probably adjusting the input to a microprocessor now, but back in the day you actually adjusted a resistance, and it can be indicated as a variable resistor in this fashion, with a resistor with a line drawn through it, or it can be a 3-terminal device, as you see here. That's a potentiometer. That's analogous to this guy here with the 3 terminals. So potentiometer, it's another name for a variable resistor, also used as volume controls, for example. And these come in various ratings measured in ohms. So you can have a 1000 ohm potentiometer, or you can have a 100,000 ohm potentiometer, and they come in various different what they call tapers. So you can actually have a linear potentiometer, or you can have one that varies logarithmically, more than you wanted to know. Capacitors, we talked about them before, that capacitors are made up of 2 plates of metal that are separated by an insulator in the middle, and with wires connected to each side. And the capacitors are measured in a unit called farads. And most of the time capacitors in the past were really small value capacitors. Millifarad, microfarad, nanofarad, and picofarad, typical metric prefixes used to indicate the value of a capacitor. And capacitors can be fixed capacitors like these, which on the top are electrolytic power filtering capacitors. There's ceramic capacitors, mica capacitors, polymer capacitors, all sorts of different capacitors with different characteristics. Some are good for power supplies, some are good for carrying RF energy, some are good for audio use, some are micro small, and with high capacitance. So it all depends on what you want. Like I say, capacitors could be a complete semester-long course at junior college. There's a lot to cover. So back in the day, I've been in this business now for 52 years. I got my novice license back in 1969. And back then, it was physically impossible to build a 1 farad capacitor. You couldn't do it. It would be bigger than a house, based on the technology that was available in the day. Well, my, how times have changed. Now you can go to Mauser Electronics and buy a 3,000 farad capacitor for $60. This was completely impossible back when I first started studying electronics. These are known as super capacitors, and they're more akin to batteries than they are to capacitors. But they can be very handy if you need to extend DC voltage from the front of a car, for example, to the back of a car. I've done this in my truck. If I have my radio mounted in the back of the truck, you can put a supercapacitor there and it will keep the voltage up right at the radio, and it works very well. So supercapacitors, just something nice to know. You don't need to know it for the test. You do need to know about variable capacitors. These were used as tuning elements in the old 5-tube superheterodyne radios, and it consisted of a stator or a stationary portion and plates that rotated in between those plates, known as the rotor. And as you adjusted the knob at the front here, you would turn this entire assembly and vary the capacitance between these two sets of plates. So the facts about capacitors: they block DC current flow, except for that really brief where we showed that bulb that would light up briefly, but normally they block DC current flow. They resist AC current flow by storing energy in an electric field, also known as an electrostatic field. Their ability to resist AC current is called capacitive reactance, also known as X sub C, and reactance in a capacitor at a particular frequency is measured in ohms. So capacitive reactance is the resistance to AC flow through that capacitor. And capacitive reactance opposes AC current. And here's an interesting property: voltage and current at the capacitor are out of phase. They are not in phase due to the creation of that electric field. I just want to introduce that to you right now. We'll cover more of that in the general class and why that's important. All right, moving on from capacitors on to inductors. And what does this look like? Doesn't it just look like a wrap of wire, coils of wire? Well, in fact, that's exactly what an inductor is. And you can have an air dielectric inductor like these are, or you can have cores. You can wrap the wire around ferrite cores or iron cores, and that will influence the amount of inductance that the inductor has. And here are three inductors in a schematic diagram. Remember, a schematic is how things are laid out and connected. And are these inductors in series or are they in parallel?
Parallel.
They are in parallel, correct. So inductance is measured with a unit called the Henry. You can easily make a 1 Henry inductor. And a 1 millihenry is 0.001 of a Henry. We talked about the metric prefixes. And it's named after this gentleman, Joseph Henry, who was involved in electronics. So inductance measured in Henrys. Inductors will pass DC current because it's just a wire. So DC current flows through it readily. But they resist AC current by storing energy in a magnetic field. So remember, capacitors stored energy in an electric field. Inductors store energy in a magnetic field and resist AC current flow, and that's called inductive reactance, or X sub L. And reactance is measured in ohms. It's slightly different than the ohms of a resistor, but analogous. And here we have a circuit with an AC generator and an inductor that is making a magnetic field, and it's changing in polarity regularly. You'll see a diagram here coming up here of a special case. So inductive reactance opposes AC current flow, and the voltage and current at the inductor are out of phase with each other due to the creation of the magnetic field. There's a lot that we covered right there. That you could go in depth with that, but that's as far as we're going to go. So if you had one inductor on one side of a core and another inductor on the other side of a core, you make a transformer. And a transformer is used to reduce or increase voltages of AC voltage, so mostly for power, for example, from the wall. So you can build this transformer to work with 60 hertz power, and you have here a primary voltage, let's say it's 120 volts, coming from the wall, and you see a large number of turns, count all the red over here, and you look over here and you've got less of the blue coming out here. So the primary voltage is 120 volts, the secondary voltage is going to be less because there are fewer turns. So this is what you would call a step-down transformer. Stepping down from 120 volts to maybe 12 volts or 24 volts AC, something like that. And then after this you might rectify it with diodes to make DC power. But this is a transformer. If you hook this transformer up backwards so that 120 volts was here, this would be a step-up transformer. And instead you might have a few hundred volts out here. So step down and step up. And in a schematic diagram, this is what a transformer looks like. What do you think? Look at the number of windings here and the number of windings here. Is this a step up or a step down transformer?
Step down.
It is in fact a step down transformer because you're going with 120 volts over here on all of these windings, and with fewer windings over here it's going to be a lower voltage. And of course here we have an AC plug, we have our single pole single throw switch, we have a fuse, which is always good to prevent overload. If there's too much current being pulled by this transformer, the fuse will blow. So I want to introduce you to one more term here that uses ohms as its measurement, and that's called impedance. Impedance is the opposition to AC current flow caused by the combination of resistance and reactance. And that reactance could be either inductive or capacitance. I'd like you to think about speakers on a stereo system or in your car. When you buy them, they have a rated impedance, usually 8 ohms. And you'll find that some of that impedance is because of the DC resistance of the wire, and some of that is because of the magnetic properties of the coil that's in the speaker. So impedance is a combination of, in the case of a speaker, resistance and inductive reactance. And impedance is measured in, as we mentioned, ohms. So there are different kinds of switch types. Some that you want to know about are the single pole, single throw, a typical on and off switch. A single pole double throw, which can maybe take one circuit that's coming in here and either switch it up to this point over here or switch it down to this point over here. So it's a way to take one circuit from one or the other. Single pole double throw. And then you can go to extremes, have double pole single throw, or the granddaddy double pole double throw. All of these switches you can use in circuits to do different things, to make things work the way you want them. Pay particular attention though to the single pole double throw and make sure you understand what it's doing. And a switch can be controlled by your fingers, but it can also be controlled by a solenoid, which will engage this lever. And in this case, it's a single pole double throw. Here's the single pole, and it either goes here or here. So a relay is an electronically controlled switch. It might look like this, but more likely it's going to look something like this, maybe in a printed circuit board, maybe in a socket that you can plug in and plug out. These are relays, which are electrically controlled switches, electrically and mechanically controlled switches. We talked about fuses, and there's also circuit breakers. And what they'll do is open the circuit if too much current is drawn. And they'll completely remove power to that circuit. You always want to use the proper size of fuse. If your circuit calls for a 5 amp fuse, make sure you use a 5 amp fuse and not a 20 amp fuse. Because 20 amps might be too much, that transformer might overheat, and you let the smoke out. So you don't want to do that. Jumping on to another topic, semiconductors, hokey smokes. But there's all sorts of different semiconductors that you need to know about. The most basic is the diode. And a diode has the property to allow current flow in only one direction. So if you put a positive voltage coming in here, it will flow through the diode and on out to the rest of the circuit. Whereas if you put positive voltage coming in this way, it'll be blocked. And so a diode allows current flow only in one direction, and the two terminals on the diode are called the anode and the cathode, and it goes back to tube days. That's what they called them. And the cathode on a silicon diode like this is indicated by the stripe right here on the side. So this is the schematic diagram for a diode, and this is what one really looks like. Now, I said this is a silicon diode. Diodes can be made of different materials. The first diodes were actually made out of germanium, and this is a germanium point contact diode. If you look at it really closely down here, it's got this little whisker which goes up against the semiconductor material. It kind of looks like an old crystal radio set, if you remember those. And in fact, that's what this is. It's a crystal radio in a diode, in a package. Interestingly, that if you put current through this diode in the proper direction and you measure the voltage across the diode, it'll be 0.2 volts DC. That's what is known as the forward voltage drop across a germanium diode, whereas silicon diodes have a 0.7 volt DC forward bias or forward voltage drop. So different diode types will have different voltage drops across them. And if you're going to use a diode, you can use them in a full wave bridge rectifier by putting 4 diodes in this configuration. You put AC in and you get pulsating DC out here, which you can run to a DC load, or you can put filter capacitors and a regulator on them, like here. Here's another way to look at it in pictorially. Here's a transformer, AC power is coming in, bridge rectifier like we just saw, filter capacitors would take the pulsating DC and turn it into much smoother DC, a voltage regulator which will make it really pure DC, and then a load. So this is a common block diagram of a voltage regulated DC power supply. And we talked about radios. A lot of radios in ham radio are 12 volt radios. This is what you buy when you buy an Astron power supply. You're buying all of these components to convert 110 volt AC to 12 volts nominally DC. Another type of diode to know about is the light emitting diode. Lamps were always the indicator of choice back in the day, but now LEDs or light emitting diodes are. And so this is how they work. You have forward voltage coming through, so from the positive going through the diode, and when current flows through the diode will actually emit photons. And you can see it. So now LEDs are the indicators of choice. So on your cell phone or a TV set or whatnot, they're not using lamps anymore because they burn out. They use LEDs. This current limiting resistor right here is absolutely necessary. If you try to hook an LED up straight to a battery, it'll burn out almost immediately. So you need something here to limit the amount of current through the LED. And remember that in a series circuit, if this is limiting current because of its resistance, the same current will be limited through the diode. So this is a standard configuration for an LED indicator. Moving right along, transistors. Bell Laboratories back in the day, Dean and Shockley were the guys that invented it. Its name is derived from transfer resistor, and an input voltage or current to a transistor is used to control the output voltage or current. So a very small input voltage can cause a wide swing in output voltage. And you can use it as an amplifier to amplify a signal, or you can use it just to turn things on and off. So a transistor can be used both as an amplifier because it has gain. That small signal can make a big signal. That's gain. Or it can be used as a switch, just turning things on and off. And the first transistors were point contact bipolar transistors made up of 3 layers of a doped semiconductor material, which either has a positive characteristic, a negative characteristic, and a positive characteristic. It's called a PNP transistor, or an NPN, a negative characteristic, positive, negative NPN transistor. This is pictorially what they look like. This is schematically what they look like. And a bipolar transistor, a standard semiconductor, has an emitter, base, and collector. And depending on the configuration, the base is typically the input and the collector is typically the output of a transistor, although it all depends on the circuit. And transistors physically look like this, and you've all seen them. In a schematic diagram, here we have a transistor here, and we have various other components. What is that component? Or that component?
A resistor.
Those are resistors, indeed. And what is this?
Capacitor.
That is a capacitor. So what's happening here is you have an AC signal. Capacitors will pass AC signals. So the AC is passed through here to the base of the transistor. It's here, it's 0.025 volts peak to peak, not very big. These resistors are set up in a voltage divider to set the voltage here that's 9 volts from the power supply, but 2.6 volts here. It's 1.9 volts here. Oh, notice the difference between the two is 0.7 volts. It's a diode junction here, so 0.7 volts is a silicon transistor. And the output is taken from the collector through another capacitor, and here the output is 2.5 volts peak to peak. So this transistor is being used as an amplifier. And likely, if you built this circuit up, it would work. Another kind of transistor is known as the field effect transistor. It doesn't have the base, collector, and emitter. It has a source, gate, and drain. The gate is usually the input, and the drain is usually the output, or could be the source depending on the configuration. These use a different configuration with N and P material, but it actually can pinch off current flow between the source and the drain, or it can enhance. There's depletion and enhancement of field effect transistors, more than you need to know. This is a field effect transistor in a circuit diagram. And here are some bipolar transistors on the input side and on the output side as well. What is this device right here?
That's a diode.
That is a diode, indeed. And a capacitor here and a battery up here. So there we go. Moving right along. Integrated circuits. I said we're going to cover the range in 2 hours tonight, so and we're doing it. So integrated circuits, I think we all know, but it contains a lot of different semiconductor devices, maybe resistors, surface mount resistors, etc. A lot of different things are packed into an integrated circuit. That's really all you need to know, but you should know about that. All right. Resonant circuits. These are the neatest thing for radio, because without resonant circuits, then we would not have the ability to tune or to discriminate between signals. And resonant circuits consist of an inductor in series with a capacitor, or an inductor in parallel with a capacitor. So you can have a series resonant circuit, and you can have a parallel resonant circuit. Those are the two types of resonant circuits. And with a series resonant circuit, if the inductive reactance at the frequency, you've got a signal coming in here at a certain frequency, if the inductance or the inductive reactance and the capacitive reactance, indicated here, are the same, and because the signals across them are out of phase, which we casually mentioned, they actually will go away. It'll look like a short circuit here at that one frequency. Now, if you go above that frequency or you go below that frequency, it won't look like a short circuit. But that is a series resonant circuit. A parallel resonant circuit, on the other hand, is when the capacitive reactance and inductive reactance are equal at a particular frequency. In this case, it will look like an open circuit at that frequency. At a frequency above or below that, it won't. And here's a graphical representation of the energy transfer in a parallel resonant circuit. You see what happens is that the energy from the capacitor is sent over to the inductor, and the inductor builds a magnetic field, and then it collapses and it sends the energy back to the capacitor, and the static field is built up, and then it collapses and it goes back and forth and back and forth. This is called a flywheel effect, and if it wasn't for the circuit resistance, this theoretically would go on forever. All right. I'm way over your head right now, and I understand that, but I want to introduce this concept to you. It'll become clear, probably not in this class, but maybe in the general class. It's a foundational circuit for radio electronics. Here's one way that you can express impedance. We talked about that speaker before in your car. You can express it with the resistance on one axis and the inductive reactance on another axis, and the magnitude is indicated graphically here. This is this is polar notation when you say its magnitude is this with a certain angle, or you can also indicate it in rectangular coordinates. Just want to introduce that to you. You don't need to know about it. So resistance is measured in ohms, capacitive reactance is measured in ohms, inductive reactance is also measured in ohms, and impedance is measured in ohms. Okay, we're making a lot of use out of the word ohm, which I know lends to confusion, but that's just the way it is. And resistance, we said by definition, is opposition to DC current flow. Impedance is opposition to AC current flow, by definition for this class. Oh, let's answer some questions. So what is the purpose of a fuse in an electrical circuit? And I'm going to go ahead and spotlight myself over here.
To prevent the power supply from damage the component.
No.
E.
To move.
So it is to remove power in case of an overload. It doesn't do anything about power supply ripple. That is what a filter capacitor might do. But no, the purpose of a fuse is if there's an overload, too much current, it'll blow and remove power.
That's right.
All right, why should a 5 amp fuse never be replaced with a 20 amp fuse?
Cause a fire.
You'll let the smoke out, cause a fire, indeed. And what describes the ability to store energy in an electric field? Electric field.
That would be
Induction?
inductance?
No. Remember, inductors store energy in a magnetic field.
Magnetic.
Capacitors store energy in an electric or electrostatic field. Yeah. And what is the unit of capacitance?
Ohm.
Nope.
Farad.
The farad. Remember, back in the day, you couldn't build a 1 farad capacitor, but now you can buy 4,000 farad capacitors. Amazing.
Right.
And what describes the ability to store energy in a magnetic field?
Inductance.
That's inductance, indeed. And what is the unit of inductance?
The Henry?
The Henry,
Ohm.
absolutely. No, the Henry.
Oh.
Inductance is
The
measured in Henrys. And what is the unit of impedance?
Ohm.
Yeah, this is our multi-purpose word, ohm. All right. And what is impedance by definition?
The opposition of AC current flow.
That is correct. The opposition to AC current flow. What electrical component opposes the flow of current in a DC circuit?
What?
Inductor.
No.
Oh no.
So we said impedance by definition
transformer.
No. We said impedance opposes AC current flow. What opposes DC current flow? That's resistance.
Resistance.
So a resistor would oppose the flow of current in a DC circuit. Now, not to confuse you, but a resistor also opposes AC current flow. So if somebody's watching on YouTube and writing in the chat, I know that. We're just going by the definitions. But that's where we start. So we're doing fine. All right. Whoops. All right. So what type of component is often used as an adjustable volume control?
Potentiometer.
That's a potentiometer, also known as a variable resistor. And what electrical parameter is controlled by a potentiometer?
Resistance.
Resistance, indeed. And what electrical component stores energy in an electric field? We had this before.
A.
A capacitor
Capacitor.
stores energy in an electric field. And what type of electrical component consists of conductive surfaces separated by an insulator? The insulator could be air, could be plastic.
Capacitor.
That's a capacitor, indeed. And what type of electrical component stores energy in a magnetic field?
Inductor.
Back to the inductor. Yep, they have them twice in here. I don't know, but it's good that we review it. Okay, so what electrical component is typically constructed as a coil of wire?
Inductor.
That's that inductor, indeed. And what is the function of a single pole double throw switch, or SPDT switch?
C.
Everybody see that? A single circuit is switched between one of two other circuits. Yep. And what electrical component is used to protect other circuit components from current overloads?
Fuse.
That's a fuse. All right. So this, I kind of like this actually. They have more of these pictorials this year. And so if you can see that, what type of switch is represented by component 3? So there's component
OBA.
3.
Single pole, single throw.
That is a single pole, single throw, correct. All right. Which is true about forward voltage drop in a diode?
Oh, I forgot.
D, it has no impact on the voltage delivered to the load.
Now, if you remember, we were looking at germanium diodes and we were looking at silicon diodes.
It'd be A.
Yep, germanium diodes, the forward voltage drop is 0.2 volts, whereas in silicon diodes, it's 0.7 volts. So forward voltage drop is lower in some diode types than in others. So what electronic component allows current to flow in only one direction?
That's a diode.
That is a diode. And which of these components can be used as an electric switch?
Transistor.
Transistor, indeed. And which of the following components can consist of 3 regions of semiconductor material?
Transistor.
That's a transistor also, the PNP or the NPN types. All right, what type of transistor has a gate, drain, and a source?
Field effect.
That is a field effect transistor, indeed. And how is the cathode lead of a semiconductor diode often marked on the package?
The stripe.
With a stripe.
With a stripe, indeed. And what causes a light-emitting diode to emit light?
Forward current.
You have to bias it forward. You have to put current through it in order for the photons to be emitted. That's right. And what does the abbreviation FET stand for?
Field effect transistor.
D, field effect transistor. And what are the names for the electrodes of a diode?
Anode and cathode.
Goes back to the tube days, anode and cathode. And which of the following can provide power gain?
Transform.
A transformer can provide voltage gain, but it cannot provide power gain.
Also the Transistor.
Transistor.
Transistor. With a very small signal on the input, you can get a larger signal on the output. And going along with that, what is the term that describes a device's ability to amplify a signal?
Gain.
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 Indeed, that's right. And what are the names of the electrodes of a bipolar junction transistor?
That would be B.
Emitter, base, and collector. And what is the name of an electrical wiring diagram that uses standard component symbols?
Schematic.
That is a schematic diagram, indeed. And here's one for us. So what is component 1 in figure T1?
A
Resistor.
Resistor.
That's A, that's a resistor. What is component 2?
Transistor.
That is a transistor.
Right.
And what is component 3?
A lamp.
Lamp.
Yep, that is a lamp in this case. And what is component 4?
Battery.
Battery.
That is a symbol for a battery in a schematic diagram. All right, moving on. What is component number 6?
Capacitor.
Capacitor.
That is a capacitor. And what is component 8?
Diode.
It's a diode, but what kind of diode?
Light emitting.
That is a
Light.
light emitting diode. When you see
Emitting
these arrows coming off of it, that's the light. And what is component 9?
That would be C.
Resistor. Variable resistor.
Variable resistor, indeed.
Mhm.
And component 4?
Transformer.
Correct. D, transformer. All right. In this pictorial, or schematic, I should say, what is component 3?
A variable conductor.
Yeah, I
Inductor.
didn't specifically talk about this,
Inductor.
but you got it. It's an inductor, the coil of wire symbol, and it's got a tap on it, so you can vary the inductance. That's a variable inductor. And what is component 4?
Antenna.
Antenna.
Indeed, that's an antenna. So which of the following is accurately represented in electrical schematics?
Components and connections.
Component connections, the way that components are connected together, correct? And which of the following devices or circuits changes an alternating current into a varying direct current?
Transformer.
No.
Oh.
Rectifier.
That is a rectifier. We looked at a bridge rectifier there with 4 diodes in it. But yeah, a rectifier converts AC into pulsating DC. We didn't go into how it does that and all of the current flows and whatnot, because that's another semester-long class. But that's what it does. All right, what is a relay?
An electrical controlled switch.
An electrically controlled switch. Yeah. And which of the following displays an electrical quantity as a numeric value?
Meter. B.
Yep, meter. And what component changes 120 volts AC power to a lower AC voltage for other uses?
B.
Transformers, so that'll transform AC voltages. Yes, indeed. All right. And what is of the following is commonly used as a visual indicator?
A. LED.
Yep. Is the power on? Oh yeah, the LED's lit. So which of the following is combined with an inductor to make a resonant circuit? So you have an inductor and a...
Resistor.
Nope.
Capacitor.
Capacitor. Remember, the magnetic field of the inductor is changing energy with the static field or the electric field of the capacitor. So a resonant circuit has an inductor and a capacitor. And what is the name of a device that combines several semiconductors and other components into one package?
Integrated circuit.
Yeah, we had that one
integrated
slide that we just mentioned the name, integrated circuit. Yes, indeed. All right, so what is the function of component 2 in figure T1?
That would be A.
No, so component 2, you see component 2? That's right here.
Control the flow of current.
Controls the flow.
So light is going to come from the lamp up here, but what this is doing is controlling the flow of the current depending on whatever the input signal is here. And if a high input signal comes in and forward biases this, then current will flow through the transistor and the light will light. So which of the following is a resonant or tuned circuit?
Would that be A?
It would be A. You have an inductor and a capacitor in series or in parallel. That resonant circuit is backbone of radio engineering. So we're going to talk about some radio circuits here, briefly, and answer some questions, and then we're done with chapter 3. This is, I think, the toughest chapter in the book. So if you can get through this, it's all downhill from here. So hang in there. We're almost done. So you've probably been in a high school auditorium, a basketball game or something like that, and they've got the PA system turned on, and somebody turns the gain up too much, and all of a sudden it starts howling in the game. So that's feedback. And if you have continuous feedback from the speakers up above to the microphone down below, we say that the system oscillates, or it howls, or it generates its own signal because of this feedback. Well, in electronics, we use that property by having an amplifier right here with an output, and we feed some of that back to the input, and by using a filter in this feedback circuit, we make it happen at one frequency only, and that is called an oscillator. It creates an AC output signal. It could be at an audio range, or it could be at radio frequencies. An oscillator electronically generates an AC signal using feedback. And so here is a crystal oscillator. We know that because this is the schematic diagram of a crystal, and this is part of the feedback circuit for this amplifier, this transistor, and whatever the resonant frequency of this crystal is, and they actually cut them to be resonant. It's a combination of inductance and capacitance in one device, and then that will determine the AC output from this oscillator. So remember, an oscillator generates an AC signal, and it generates it on just one frequency. And filters, I mentioned, are used in the feedback circuit to reject unwanted signals, or to allow certain signal frequencies only. They can be wide, they can be narrow, they can be band pass or reject. You'll learn more about these as we go along. They can be as simple as a resistor and a capacitor. And this is what's known as a low-pass filter, or there can be a high-pass filter with a capacitor in series with a resistor. And on a graph, low frequencies are passed, but higher frequencies are blocked. That's called a low-pass filter. And the reverse, low frequencies are blocked, but higher frequencies are allowed through. That's a high-pass. Just introducing these terms to you for future use. So a transmitter consists generally, this is a Morse code transmitter, of an oscillator. We've said that an oscillator generates an AC signal, and a driver amplifier, which amplifies us up to a higher power level. We may have a Morse code key that controls both the driver and the power amplifier. The power amplifier takes this maybe 1 watt signal up to 100 watts, and then you can take it out to an antenna. So we're using an oscillator to generate the AC signal, amplifier stages to increase it, and then a telegraph key to modulate the signal. Modulating a radio frequency carrier adds information to that carrier. If you just transmitted an AC signal without turning it on and off, that would just be a single carrier. You don't know what it means. There's no information on it. But when you modulate it with a telegraph key, that's one way of adding information. Another way is to add audio. So if you have an audio tone, a low frequency audio tone, and you have a higher frequency radio frequency carrier, well, if you vary the amplitude of that radio frequency carrier in step with the modulation, this is called amplitude modulation. And you can see here that the peaks and the valleys here correspond to the peaks and valleys of the AC modulating signal. So this might be at voice frequencies, this might be at a radio frequency, and here's an AM modulated envelope of that radio frequency. Or we sometimes talk about FM, or frequency modulation. You can see here's the carrier, and you can see the frequency of that carrier is changing. Lower frequency, higher frequency, lower frequency, higher frequency, in step with the audio or sound that's coming in. So here's an AM signal, and here is an FM signal using the technique of modulation, adding information to be carried on a radio signal. And in an AM transmitter, like a broadcast transmitter, they have a master oscillator, driver amplifiers, and a very high-powered radio frequency power amplifier that is modulated by an equally powerful audio amplifier. This is called brute force modulation to generate an AM signal. In receivers, receivers too also have all of these amplifiers and oscillators and other circuits. The most common radio is the super heterodyne radio. We won't go big into that, but you have a radio frequency signal coming in, and it goes first to a mixer stage. And the mixer stage is connected to an oscillator that you control in the radio receiver. And by controlling this and mixing the input signal with the oscillator signal, you actually change frequencies down to an intermediate frequency, which can then be amplified and detected and taken out as audio. So a mixer is used to change one frequency to another. And so you have the radio frequency signal coming in, your local oscillator signal coming in here, and the desired signal coming out there. You actually get more than the desired signal. You get both the sum and the difference, but those can be filtered out. And here's mixer math. You actually get 4 outputs from a mixer, but really we only want one of these, and that can be filtered out to use for amplification. And a demodulator is the thing that captures the information that was originally modulated onto an RF carrier. So in this radio we have the signal coming in, we have a mixer to change it down to an intermediate frequency, and then it's demodulated and output as audio. So that was a blitz look at radio. We'll do more at a slower pace, but that's the way this chapter goes. Let's answer some questions. So which of the following is used to convert a signal from one frequency to another?
Mixer.
That's a mixer stage, indeed. And what is the name of a circuit that generates a signal at a specific frequency?
That'd be an oscillator.
That is an oscillator. And what is the name of a circuit that, oops, hang on. Which of the following describes the combining speech with an RF carrier signal?
That would be modulation.
Modulation.
That's modulation. That's adding information to the radio frequency signal. And ladies and gentlemen, you've done it. That is the end of chapter 3. I am so proud of you. We have made it through tonight. Are there any questions from anyone before we go tonight? Very good. All right. So this weekend I'm going to be busy. I'm going to be away at a ham radio convention in Pigeon Forge, Tennessee. But I'll have my laptop with me, and I'll be sending you out a update email with information about the next chapter, chapter 4. But until then, thank you for being a great class. So happy to have you aboard. And we'll say 73 and see you next week for chapter 4.
Except
That's very good.
Goodbye.
Thank you.
73.